Mikhail Gromov from the IHES will talk about combinatorial and homological ways of infinite groups.
Okay, so there are several kind of lines of thought I was pursuing a long time ago, and so I just say something about that, and I dropped doing that mostly because I couldn't do much. There was some progress meanwhile, and possibly I might say something as questions, conjectures which had somebody had answered, so you'll tell me, yeah, you will not offended. And so what are the main line of thought in there? So let me enumerate them at about 3 or 4. So we have to start from here. So now number 1. So we have group gamma. So it is an infinite group, and so subject to our study. And 2 general questions about that. Are there kind of naturally, functorially defined geometrical spaces X somehow related to this gamma? So the geometry of this X respect this gamma. And it's number 1. And commonly, what you do, you take what the people combinatorial at the end that people call Cayley graph, and then it has some geometry. Of course, geometry only up to choice of generators. There is some ambiguity, but then a posteriori, you know that if the group is special, and this is coming from most originator theorem, a group of fundamental group of hyperbolic manifold, then in terms of group itself, you can recover this hyperbolic space, and so there is unique space, geometrically, functorially, canonically defined from this group gamma, and so it's one of the constructions, and it works quite remarkably well. But there are other constructions which I will be discussing here. So we want to construct a space. It's number 1. Another related topics, of course, it will be kind of somewhat the opposite from the group. You can go to algebra, and for example, maybe some group algebra or group algebra with some extra structure, and again, you want to transport or translate some geometric property or algebraic property of the group in terms of this algebra, and then this algebra again some geometry enters. Now, the basic things behind geometry, of course, how you go from geometry from group theoretic properties to geometry. The basic in geometry are certain numbers, and this kind of hierarchy of numbers, starting from this cardinality is kind of level 1. Level 2, you feel the dimension. If you linearize a problem from cardinality, you go to dimension. But in geometry, so this is one direction. And that is maybe something like volume or measure. And then there is transcendence degree, which doesn't seem to play a role so far much. Or there are some other dimension type invariant, like phenomenon dimension, and then it goes to K-theory of sister algebras, which again express the same idea as volume dimensional cardinality. They have the same formal behavior in categorical terms. And this is what we, though these arrows are different, they may have very similar next step. So when you count this geometric object or the algebraic object, you start study it using this as your measuring means. You measure this kind of characteristics. It's number 1. And another subject, this kind of factor idea is whenever you have such an invariant like volume, geometrically volume, and then or cardinality or something of that kind, you again following the principle, basic principle of category theory, you don't look at individual objects, you look at families, or you look at morphism. And then you have to assign similar invariant to a family. And one, traditional one in metric spaces is Urison width, when you map one space to another. You have space X over Y, and you concern is pullbacks of the points. So your object now pull back of a point, and you look at this invariant of that, whichever nature it can be. It's numerical invariant, which depends on Y. Now you have function of Y, and out of function you want to extract number again. And if you were a physicist, you would integrate and say, take some kind of average, and usually which makes no sense in mathematical sense. But mathematician, we take supremo infimum. And this is, of course, very, 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 very wrong thing, but you don't know how to do it otherwise. You know, Mandelbrot, who introduced his Mandelbrot dimension, this pointed this very well, that there is Hausdorff dimension of space, but this, in a way, meaningless concept, because it depends on taking phi or supreme, and you know there is no way, you know, monotone function converge, but you don't know how fast they converge. And then there is fractal dimension, but there is some extra structure, and it's actually a limit of something, and this limit can be at least approximately computed. And this kind of physical concept. I don't know what will be here later. So that's of course, if you, on the next level of sophistication, taking this, usually we take supreme of that, or in film of that, we don't know how to do it. And in second, they say where it comes from in geometry. It goes back to Birkhoff's proof of existence of geodesics on the spheres. It's a very old story. And it was Urus and Weiss on one hand, and then there was Birkhoff argument elaborated further. It's number 3. And the number is 4. Number 4, I'm sorry to say in Russian. And number 4 is, point is about the following kind of phenomenon. First, probably explicitly elucidated by Thurston, that if you have a hyperbolic space, compact hyperbolic manifold in a certain sense, then its topology bounded from below by the geometry. If it is in any way the space is large, then topology must be approximately complicated in being proportional to the volume of the space. And it was not explicitly, but not explicitly, but was in the work of Thurston. It is number 4. And so it's on one hand. On the other hand, just look at the last issue and what will be questioned. Yeah. So a specific question, which I wrote in my paper about hyperbolic groups, and then I found later on a mistake, and there was much weaker conclusion which I could make. And then there was the work by Delzand and Avramidi, when they proved much better, conceptually much better result, but still very far, I guess, very far from the precise one. So I'm going to formulate the problem, and it is okay. We use this. So we have a manifold X. Maybe if you're not so much for manifold, maybe combinatorial space, but it will be with negative curvature. In general, so I confuse myself about this, what means what, yeah. Cat minus 1 space, so it's a space of negative curvature, and it's locally sufficiently large. That means the displacement of all non-zero elements are bounded below by some constant R. Or equivalent, you can say in geometric terms, injectivity radius of this manifold, at least at one point, or even better, at all points, bounded by a constant R. And then there is a number depending on this R, possibly on the dimension of the space, probably not, such that every subgroup generated by less, so any subgroup generated by n less than n element is free. Right? So if there are big balls inside, which are, I've seen topological in geometric sense, just topological balls, or if it is in a more general space with positive curvature and all transformations have big displacement, then subgroup with few generators must be free, which is generalized, of course, the case when that if you have a free group, then all subgroup of free groups are free. The question is, what is this? How this depends on that. And originally, when I thought about that, I said that it might be exponential, right? That n of R must be around the x power. Might be some exponent. But when I was using that, because I just wrote and I gave kind of sketch of a proof, but when I was using it, I observed that the proof only gives you an estimate of this n of R, like R over log R. I wonder if something was done since. Right? Of course, x of y is because it's a volume. This is for what you expect in all the examples how it works. The argument like that. And now recently, well, relatively recently, there was a paper by those two guys, Avramidi and Thomas Gazan, when they proved much finer result but with a poorer estimate. And what is the result? So again, I repeat, we have a space of negative curvature at least minus 1. At one point there is a ball of radius r, which is a topological ball, and then every subgroup generated by n less than, and there it was a constant n type square root of n, square root of r. Elements, not only this group is free, so it's square root, but if you take the ideal, any ideal in the group algebra of that, generated by so many elements, this ideal will be free as a module over the whole group algebra. That's the result. Right. So it is much finer result. It concerns this group algebra. It implies, of course, the case of freedom of the group, but its estimate is still square root even worse than that, and so it's very far from exponential. Right, and this says very nice corollary, and this the same corollary exists here in purely topological case, but the corollary I want to bring in because it's kind of a very attractive theorem which has many links with other results. It says the following: if I take this manifold again, I believe in their formulation and they need this to say I'm quite happy this being for the case of a manifold for negative curvature, even for constant negative curvature, is quite nice, where all balls, they assume all balls of radius r are topological balls, or all loops are long. Then in every dimension, this manifold has dimension, say, d. Then in every dimension, if you take a Morse function of this manifold, or you take any cell decomposition of this manifold, the number of cells in every dimension will be of this order of magnitude. It will be about n. So again, this dictum of kind of proposed by Thurston, that topology grows proportionally to the amount of curvature manifold case. But here it must be kind of having this big box. And you know, it's not true if a manifold just grows, and it may be not true. For example, the manifolds which fiber over the circle, and you know all hyperbolic manifolds fiber over the circle, they're cyclic coverings. The number of cells in every dimension doesn't change when it takes covering. Complexity grows for another reason, because there are automorphisms in the group. And this is very exceptional, very pathological phenomenon. So for all we understand, this happens in very rare cases, like though three-dimensional manifold is an exception, completely different from what happens apparently in higher dimensions. But under this condition, if you have manifold and the injectivity radius grows, so displacement of all the main grows, and morally it means that cohomology with some coefficient, their rank must grow. But this coefficient, we don't know what coefficients are. They kind of only with essentially coefficient with a group ring or something. I'm not certain what are the right coefficients. But the number of cells growing, and this proven following like elaboration of the statement I said before about freedom of this moduli in the same way, and which is more or less entered the game here. And so the issue which it brings first, if the estimate is square root of this radius is correct, because we expect to call it exponential. And secondly, well, how much you need actually negative curvature? It's certainly true. If you look at the products of manifold negative curvature, which are already have non-positive curvature, or for higher order symmetric spaces, it's probably true in all these cases, and there are some good indication where it should be true. Well, it's unknown. Okay. So most of what I'm saying, of course, is just I remember more not the result but the problems, because problems I think still unsolved. Right? I don't know if somebody knows. If you know it, something was done in this direction, we'll be happy to hear that. Or I'm happy to hear that. It's the issue. Now, what are other results of this kind? So what is the measure? What is the measure of complexity, of topological complexity of manifold brought in? And this is a very nice invariant, very naive invariant. If you have any topological space, actually you only care for its homotopy type, and you ask how many cells you need to build this space, build up to homotopy equivalence. And how many cells in every dimension. It may happen that you can trade cell in one dimension for the trade of other dimensions. So it's a whole spectrum of numbers associated to the space, and the number can be varied. So I have quite amusing invariant. Even this, okay. X defined up to homotopy type. Even manifold, you can speak about Morse functions and see how many critical points are there in every dimension. If you don't care for that, just how many cells are there. And from group theoretic point of view, and this is how it's done in the work by. Okay, I have to do not to stop here, right? Done by Avrami Dilzan, they of course use resolution. And look at the free resolution of that of a group ring and just see what the rank of this to the minimum resolution, it must grow in certain ways. And this. Okay, so what we can say about this invariant? You see, it came up from simply connected topology by the work of Smale, mainly, so that you can construct a function with few critical point providers, and topology is right. But the case of non-simply connected manifold is much more subtle. It kind of reduces to group theory essentially by the work of Paul, but reduction is a fiction because it just says, well, all simply connected stuff, all this reduction kind of trivial stuff, and it just the difficulty starts from the group theory. Yes, this kind of you reduce what was at some time the major focus, when you made in the focus of topology, now consider the obvious and the non-obvious part resides in the group theory. So, but what is known about that from a different perspective? So let me state another theorem, which is, in this paper of mine wrote a while ago. It is a very simple interpretation of my ideas going back to Lucy. It is, and the question is as follows. So I want to give a more kind of elegant, kind of more stable definition of that. So now we have a manifold, preferably orientable manifold, some dimension n. It was d, now it's n. And then I consider other manifold, say, call them x d, which go there with degree d. There's manifold closed, orientable manifold. And then in here I look what is the number called volume sigma of this xg. And volume sigma meaning the minimal number of cells needed to make cell with the composition of the space, or the minimal number of critical point of Morse function on that, depending on this manifold now. And then I take infimum of all these numbers over all x and all f. So and then I'm sorry, and I divide this by, this is number of sheets. I didn't say how many it is yet. So I can maybe put here something n, and here is a number of sheets, and so I divide it by, of course when I take covering, you expect volume to be proportional. If it's not, so as for it, I just divide, and as usual, subadditive function, there is a limit, so it's normalized. It will behave formally like the norm. Right? And the question is if it's ever non-zero, right? Or given from 1, depending how you normalize. So if you have a manifold, you don't take a covering. If you take a covering, of course, if you knew the early characteristic were non-zero, or the signature were non-zero, then after taking a covering, this multiply, and the number of cells will grow proportionally. It's no fun. I mean, it's fun, of course, but it's easy. But here you take any map of certain region. So it's really completely distorted topology. And you know a simple case when everything behaves as you expect. If you have surfaces of higher genus, and you map another surface in there, then the genus increases, early characteristic now, normalized early characteristic, and the genus multiply at least as much by how many sheets there are in this map, what the degree of this map. So if we have this degree in this thing with degree 10, early characteristic will be multiplied at least by 10, even more, because some part under this degree may collapse, but still there will be essential part which grows. It is a product for surfaces. This is easy case, I mean, undergraduate course of topology, but already if you take product of two surfaces, it's also true, and this is already non-trivial. I mean, non-trivial, I don't know simple elementary proof, and the proof relies on the index theorem for the signature operator in some particular vector bundle. So we have to use a distinguished vector bundle kind of spin bundle, major bundle, square root of the tangent bundle of the surface, and using this you can prove that. And there is a score of other spaces with similar properties, namely all locally compact, locally symmetric spaces of non-compact type, meaning non-positive curvature, where the early characteristic is non-zero. So the covering do have this property. So if you cover them with so many times, with so many multiplicity, then you multiply this number of cells at least proportionally, but the same is true for any map into that. So you map any manifold with degree, with a certain degree, but and this number of cells grows by this degree. And it's unknown in kind of how many spaces it applies. It doesn't apply to odd dimensional manifold of this kind, yeah, because none of them, of course, has zero. They all have zero early characteristic. It's definitely true for dimension 3 because of this circle bundle example. Now there are some examples on dimension 5 which are not compact, but this is minor issue. But then in higher dimension it's unclear, so it happens, and even in dimension 3 or even in dimension 5, there may be some simple conditions that would still bring this property. Because if it fails, this seems to be generic property. If it fails, there might be some very particular reason there, something very special. Like in general, you know, the hyperbolic groups are kind of very rigid, except when there are kind of surface group or some pattern of surface group inside, yeah. And this is the work of ellipse, yeah, some coauthors, Zella. The group are very rigid except in lower dimensions. And so all non-rigidity may come from possible non-rigidity and existence of non-trivial automorphisms in lower dimensional hyperbolic groups. But we don't know in general what happens. Okay. So that's the problem. And so maybe I say just a few words about this reason what I said some index theorem, but what actually, before you apply index theorem, you have to reformulate it in a different way. And point is, again, you go to the group algebra. But now, when you have a manifold and have a group algebra, you come and look at this, and we have some cell decomposition of this complex, and then in this algebra, if manifold has dimension 4k, then there is well-defined quadratic form there. Namely, you can just intersect cycle or multiply co-cycle, evaluate them on the whole class. So it's not only just homological product on cycle and co-cycle, and which is bilinear operation on the group algebra, because group algebra X in the universal covering, X on all that. So what you have, quadratic form, I'm missing some point of the structure, but essentially it's quadratic form over the group algebra of manifold. When you have a quadratic form, it has an essentially invariant. Out of quadratic form, you can make the Witt group, right? No, if there are Witt, it's a quadratic form, and you have some trivial form which kind of the same form and formally minus this form, and then you can add them, and so they have this Witt group. Okay, and this is a Witt group. So one of the fundamental issues in topology and in group theory is that if we have a manifold, a spherical manifold where there is nothing but this fundamental group, say for dimension 4k, and I take this element in the Witt group, exactly, I take this. This say over real coefficient, be careful, but it's essentially what I'm saying. Essentially correct. We have quadratic form over this ring, and it's the question if this form after some transformation, change of coordinates, can be decomposed into some form plus the same minus the same form, and the element trivial element in the wheel group. So kind of signature is 0, and this is unknown. If it's two others. And this is a kind of special case with the so-called Novikov conjecture about high signatures. And this is the most elementary instance of that. So this is purely group theoretic question. Repeat, we have a group, and it's such that it is a fundamental group of a spherical manifold, which can be formulated in a purely algebraic terms. There is some kind of Poincare duality in homology, or all kind of universal physical homology. And then, if it's a dimension not 4K, there is slightly more delicate definition invented by Wald. How to define it was essentially if you have any manifold multiplied by itself 4 times, and this equation stands for this usual, well, a wheel group. So why this element is non-zero? And the difficulty is we don't quite understand how we change coordinates. See, because it's, when you compare to quadratic form, you can change coordinates and then can add them. Adding them is easy. But changing coordinates over some staying group ring, who knows what happened there? And so the thing will disappear. And that's a big question. It's known for all known groups, more or less. Novikov conjecture was proven for a huge number of groups. And so this, but the point, the key example, the key issue, the key instance of this conjecture, what I said, but now you want to slightly more. Now you consider this width group, you consider the rank of them to high and high and high. Right? And then you divide by the rank of the group. And then you go to the limit. So you have reduced wheel groups because you kind of stabilize it. So you would kill the torsion, so to speak. And still you ask if it's 0 or not. And then there are manifolds, there are groups. For example, if you take fundamental group of even dimensional manifold of constant negative curvature, this is still non-zero. But if you have odd dimensional manifold, it is probably 0. It's 0 for dimension 3, likely to be 3 for dimension 5, but then become very unclear if it's 0 non-zero. Right? So it is and the proofs of being non-zero all depends on the index theorem, because from this wheel group you go to some completion to some infinite dimensional algebra, and then this signature can be represented by some elliptic direct type signature type operator, and then you compute this index non-zero, and then you prove that Novikov conjecture. It's a kind of remarkable idea going back to Lucic and Mishenka. And from what it follows, and there is another ingredient in what I said for manifold of coordinates with curvature here for the surfaces. As you do that, for higher dimension, you need some particular representation of the fundamental group. So you can apply this index theorem, and actually, when I wasn't unable to construct it, but it was kind of clear it should be there, and I knew whom to ask, and it was Lucic, and he immediately said, "But the research representation, that all you have fundamentally the group, and there is a technical term to say there is discrete series in representation, then there is a very particular kind of dimensional representation with some nice properties, and they're classical, of course, and Lucic pointed out to me. They have, of course, never understood the property. So this depends, but it crucially depends on the existence of very special representation of the group. So if you slightly modify this group, and so you make some surgery or something, and you kill this particular representation, we don't know what happens. Either this have a 0 or non-zero. And this, of course, closely related, I guess, to this work by Remagen and Delzon. So possibly what they do on a high level will also bring in analysis, or maybe on the contrary, my intuition when I heard about the theorem was to prove it elementary by geometrically, and I couldn't do that, but still I haven't thought seriously yet. Maybe there is purely geometric argument in the spirit. We do it for just freedom of subgroups of these few elements in these manifolds. So this is one topic, right? Now, so what was the second topic? Number 2. So here we mostly were saying about what happens when you linearize. Now how we can geometrize. So what are natural geometries, natural spaces, canonically defined by the group? And then, so you know that a posteriori, because of the rigidity, or most of the rigidity, this is for all locally symmetric spaces, this space uniquely can be described in terms of group. Though saying it precisely is not quite clear. And there are several ways to proceed. Yeah, how out of the group you can construct a space in a canonical way. And so one, I say a few words, I don't elaborate much on that. One is using the dynamical approach, the symbolic dynamics, because this group acts very intensively on some compact spaces. And this action can be built, reconstructed out of the group. And this kind of ideology goes from how symbolic dynamics apply to hyperbolic systems, starting from the Wolf-Sumer and Anosov. And this applies to almost to all groups and shows that space where they act topologically, canonically reconstructible from the group itself. But this is not what I want to say right now. This gives you canonical topology, but it's not so clear how to go to canonical geometry. On the next level, we have to say there is canonical geometry on this space. And this is not so clear how to do that. And another way to do it is following the kind of classical idea, going back to Bergman, how you construct Bergman metric on complex manifolds. And specifically, besides spaces where you do know there are canonical metric, like locally symmetric spaces, there are other kind of special spaces, rather special, not absolutely canonical, where the fundamental group kind of reconstruct them canonically and uniquely. And this idea of a Bergman metric. Now, when you have a complex manifold and how given a complex metric, a complex manifold without any additional structure, construct a metric on the space. And if it was acted upon by a group, it will be equivariant action. And this construction also depends on passing to some linearization, to some space, and then from this space extracting geometry. Okay? So what is the Bergman construction for complex manifolds? One, and this in principle is very general construction, but in the case of complex manifold, it gives you kind of nice way to do that if it works. So you have a complex manifold and the group acts on it. Now it is a complex structure. How to make it symmetric? So what you do, following. By the way, interestingly enough, once a long time ago, I met Salman Bochner, who was then in Texas, and he said that this was his thesis actually. His thesis, he constructed Bergman metric. And this written somewhere, so a few years before Bergman. So you have the space, complex space, in a group of arrays, complex space. So the space is interesting space. Usually there are not many holomorphic functions there, especially the L2, which are interesting here. We look at the holomorphic forms, holomorphic top-dimensional form. And so this is some canonical space, and sometimes, if you're lucky, you have a non-trivial L2 space of these forms. If you have group action and there is one L2 form, so for fast decaying something, there are many of them, there is infinite dimensional space, and because they are form, if you take form times its conjugate, you become usual form, you can integrate it, and you have Hilbert form, right? So this form times conjugate form, you can take scalar product, so you integrate. So it's a Hilbert space. Right? It's beautiful, right? You get Hilbert space of function. Okay, this is just space, just linear space, so what's the fun, right? There is no kind of metric there. But what you do next, you map now your space to the projective space over this space. Namely, to each point there, you consider all forms which vanish at this point. And so it will be hyperplane in the space of all forms, so it's projective space. So you map your manifold modular group, because it's equivariant, into the space. And so it is represented by complex manifold inside of the infinite dimensional complex projective space. And this kind of quite remarkable simple construction. And then it raises very general kind of question, how far you can go with this in general. And by the way, if this is everything in Cayley geometry, so you know, from geometric point of view, this usually have minimal volume there. So you have this infinite dimensional projective space acted upon by a group. It's a kind of rather bizarre space, right? It looks quite strange. You have kind of bounded space divided by the action, by discrete action, more or less. It's essentially discrete. And in this new space, there is this locally Frobenius studio geometry, standard infinite dimensional geometry, and then you look for minimal varieties. Of course, when you start minimal varieties, you're slightly careful how you define minimality. You have to do it slightly more carefully. But nevertheless, this is a Bergman idea. And but then for other spaces, so what you may hope to achieve in this way, you obtain it this way. So besides this most of the rigidity theorem, which is known as European group theory, there is a next version of that, which is a more general and in some sense more profound, is a rigidity theorem U to C. It concerns complex manifolds. And it says, in effect, that if you have a now complex hyperbolic manifold, and you have other complex, and I was saying a little bit personally, slightly vaguely. If you take another complex manifold and to map there, then it's always homotopic to the holomorphic map. You have to say under what conditions. Like if you have another, say, Kähler manifold, and you have a map between them and some condition, it's not very, it's sufficiently non-degenerate, so topologically it doesn't contract to something lower dimensional, then it actually comes from complex submanifold, and in particular, if you have a hyperplane, you cut it by hyperplane, and so it will be some hyperplane section of that. Now, now immediately you say, aha, by Lefschetz theorem, when you take hyperplane high-dimensional complex manifold, fundamental group doesn't change. So your complex manifold, the big locally symmetric complex manifold, was uniquely representing your fundamental group. But now if you have a hyperplane section, and there are lots of them, they move, yeah, they appear in moduli, and they change. Even the topology may somewhat change, well, not very much, except for singular ones. The geometry complex structure changes, but they still have the same fundamental group. So the object which represents a fundamental group is not one space, but a family of spaces. It's a canonical family of spaces with some geometry. And this is, we have to have in mind. If you want to construct this and do this for more general situation, you must be aware of this kind of phenomenon. You don't expect to have unique space, but rather a family of spaces. And the question is, what are these families? Now let's try to look at this from a different perspective. How you can do that? So here, so what we were doing, it was the point was, you start with your manifold, with group action, then you have some space of L2 space of something there, maybe sections of some bundle, natural bundle of functions, and then I divide by that, and then take this Bergman embedding, and then inside there I look for some distinguished finite dimensional submanifold, and because this manifold represents some definite homology class, I look for minimal homology class in this space. And the method is pursued by some, yeah, in some cases. And so, but how we can see this geometry, the first step in a more general case. So there is another construction which similar somewhat in the result, although looking quite different, how from a group you can construct infinite dimensional space with a kind of family of geometries, where you can pick up any one of them and just play with any one of them, but probably all of them should be considered simultaneously, and we again immediately run a bunch of problems, open questions. And this is what you do with this focus. First, what you do, you forget essentially you had a group, but you have any nice topological space. Nice meaning no fractal, no nothing. which is locally contractible space. And if it was a group, gamma, what you do, you look at the K by 1 space of gamma. My notation is the same, classifying space for gamma. So it's a contractible locally, it's contractible space divided by this gamma. So it's when the universal covering of this is contractible, and gamma acts there. Or another way to say it is all homotopy groups are trivial except for fundamental group being gamma. So this space is unique up to homotopy equivalence. So I have homotopy type. Now, how from that you can construct family of matrices. Now the major kind of way to see, to kind of geometrize the space, you consider kind of the semi-simplicial, people say the semi-simplicial complex that which I always have difficulty understanding, but what you essentially consider, you consider maps of all simplexes in this space. And then, whenever you have, say, 2 points at the simplex, you have a path, you join them by a simplex. Whenever I have this picture, I fill it in by some map because, if you can do it, such a representative exists, and then they do all of these maps, all meaning all up to homotopy. They all must be careful which cardinality you choose. Maybe countable, uncountable, say all countable in all homotopy classes. Then you come to the simplices of dimension 4. Again, imagine you have boundary of those. And again, in this space, you consider all possible map of the simplex. And so I have huge simplicial complex. It's not exactly simplicial, but you can pretend it's simplicial. It's a huge space built out of simplices. It's infinite dimensional, infinitely many simplices. But then you have lots of geometry there, because for a simplex, even a simplex, there are many natural geometries there. Of course, the pleasant geometries are flat geometry, as you know it, or you may take spherical geometry, part of a sphere, or part of the hyperbolic space. And this is kind of 3 natural geometries. But in a way, well, there is no reason to forget other geometries, especially when we go to high dimensions. Point number 1. Secondly, simplices are not sufficient for this purpose. For example, if you multiply spaces, simplices don't quite multiply. You have unpleasant thing. So you have to allow, of course, not simplices, but also product of simplices, for example, cubes. And cubes have their own spectrum of geometries. Multiply simplices at one geometry, and then they have their own geometry. So they have collection of all these geometries, and they all live in the same space. So there is a unique kind of family of geometric spaces, kind of almost Riemannian, infinite dimensional, representing your topological space, and if it were K per 1 specifying space of a group, something related to that. Okay. So we have this, and this is a similar geometrically to what I said when you have this Bergman projective space or sphere divided by a group, right? If you open it, it's very kind of similar, but not exactly the same. It's similar, but not exactly the same. And then the moment it is done, you say, now I have this space, infinite dimensional space with geometry. It's that kind of Riemannian singular Riemannian manifold. Right? And then, what about my manifold? What remains of the manifold? And my manifold, if then there's some fundamental class of the manifold becomes homology class in this manifold. So the classifying space of the group, of course, there are many other homology classes depending on the group. And they're kind of quite of interest, especially if a group was coming from Cayley geometry, when there is fundamental Cayley class its power. But if it's just constant curvature, the only distinguished class, fundamental class. So you have infinite dimensional space, and inside of this space there is homology class, and this homology class is geometry. So what, of course, you want to represent it, the kind of instinct of a geometry, take a minimal one with minimal volume with respect to this geometry. And if you do it, for example, if you use hyperbolic simplices here and do that, and then reconstruct a complex hyperbolic manifold. And sometimes you'd better take spherical one, and this was sound was studying in the latest papers. So what happens in this case? And before, just certainly one thing you reconstruct it, and another thing you extract this invariant, the volume of that. And this is defined, observed purely topologically. So you start with complex hyperbolic, it's kind of say, a real hyperbolic space, apply this construction purely topologically, and then take minimal class and take this volume, and you reconstruct the volume of manifold. And this is kind of a property of that. And this volume depends, of course, on how you normalize the geometry in the simplex. Maybe flat simplex, hyperbolic simplex, spherical simplex. You have a variety of possibilities, and you have various numbers, and you have various geometries. Or you can take cubes, and you have another number. And it's very unclear what the relation between these numbers. So again, the question is, for example, if you use cubical object and standard geometry, this invariant multiplicative and the product of spaces and product of groups. There is inequality in one direction. If there is equality, it's unclear. So it's easier to make this definition, and sometimes nice to prove what I said, that they give you the right numbers in simple cases, but how they behave in general, I don't know. That's one. But in any case, this volume is a something, or what you mean, of course, you want to relate it very much with what I said before. Instead of this volume, which morally measures the number of simplices needed to triangulate your manifold with some correction on the geometry, and you can expect it to be always bigger than the number of cells needed to decompose your space. However, it's not clear if it is true. So there's two invariants, they're different, and indeed, this always multiplicative. It's actually behave like volume. It's multiplicative under covering and semi-multiplicative under maps to certain degrees, norm and homology. But its relation to what corresponds to cell decomposition is not so clear. Strangely enough, and there is no direct relation of that to analysis, to L2 homology. Although recently you told me there are some relation of this type. Yeah, you can relate in some cases the simplicial norm to the behavior of the Dirac operator. Yeah, so but this is just a paper is still unpublished, which I haven't seen, so I cannot say much about that. Okay, that's another topic. Now the last one, which appears in the title of my talk, it's about waste. I already said a few words about that, and now I have to conclude with this. So this is some mechanism how we generate interesting invariant, how starting from a group, acting on a natural space, for example, we construct the geometry of the space out of the group itself, forgetting temporarily the space, and then reconstruction. But now what are the invariants you want to know? And I said you have this a natural example coming from algebraic geometry. We always have moduli, and there are families, so we stick to families. And so whenever we have some invariant, we want to have this version for the families. And here is the question. So I'll state some theorem and then formulate some question. So I formulated it quite simply geometrically, but then we related to the more abstract setting. So I have a manifold of negative curvature again, and again it has big injectivity radius. So the answer will depend on this radius. And then I consider family of objects in my family, so it will be manifold of dimension n, negative curvature, normalize radius, and there is radius up, no number. And this is mapped to the Euclidean space of dimension n. I prefer to write it this way, n minus k. So fibers will be something, this fiber is something k-dimensional objects. And you want to relate topology, topology of these fibers to geometry of these fibers. And one kind of essential observation in this context, going back to Thorsten, that if you have individual Ktashev fiber, and you know this fiber can be triangulated say in n simplices, so it has such a slice, it triangulates in so many simplices, it has dimension k, then you can homotop it to a new map where the volume will be bounded by a constant times the number of simplices, which is actually, you know sharply what the constant is. Because in hyperbolic space, all simplices individually have volume depending only on that combinatorial structure, but they all have bounded volume. No matter how long the size, they still have small volume. And this for individual one. But if you have a family, and now imagine, you know that all the simplices, all the slices can be triangulated. Imagine the map is combinatorial, simplicial map. So all these fibers are simplicial complexes. And imagine you know the number of simplices in all of them bounded. And you want a posteriori prove that there is a fiber with a complicated structure, topological complicated. But because you have this negative curvature condition, and without even this relation. Now for individual one, you can make this contraction and make volume small. Can you do it for family? So can you deform the whole thing so it will happen in all of that? But the construction which is used in this straightening of the person doesn't apply here. Except, which I could do it in dimension 2. In dimension 2, it does apply. And this is a rather technical argument, which again, rather unpleasant, which I wrote down in this. It's kind of obvious, except you have to check it works correctly, because it's kind of obvious for all dimensions. But then it happened to be clear, which I couldn't prove. Which again, just straighten the simplex, do it simultaneously, but you get it, except when they say simultaneously, there is some problem when you take automorphism. This operation is not kind of functorial, sufficiently functorial. And then the consequence of that is that if I have such a manifold where also, for example, injectivity radius of large, and I make this combinatorial map, then only the nk equals to 2, and this is the only case I couldn't handle, then you can deform this map and deform this family, not the map so much, but you deform the whole family, and so that all simply straighten up, and you have slice of small volume. But because injectivity radius is large, you know the volume cannot be small, so there is lower bound on this kind of a parametric number of simplices in these fibers, kind of this simplicial waste of this in dimension 2 will bound from below. This is so what you can do. And the issue is if this is true for higher codimensions, if it's true for all k, and it's unclear. And next question immediately arising in this period is in the paper of and the result by these two people. Does want to come up? Okay. So it is by Auramidia and Delzan, if the same is true for families. So everything, apart from their paper, which I have studied well enough, so I can judge, but the logic of everything else, this should be true. Not only you know that there is a fiber always which appear with small number of simplices, but even a fiber with small number of cells in any cell decomposition. So the topology of the fiber will grow. So that's the question which I want to finish. I think it's an amusing question to resolve. Okay, finish.
Questions?
Yeah.
So, this is a question from a former geometer became statistician. Okay?
No, I'm sorry, I missed what you asked.
Okay, so
Acoustically.
question is,
Yeah.
In statistics you need spaces that are homogeneous. So the question is for what are the conditions for, let's say, a three-dimensional hyperbolic or all the homogeneous hyperbolic three-dimensional manifolds?
No, you see, what I was saying was only tangentially related to dimension 3. Dimension 3 in many respects is exceptional. So just if you want general results of this nature, you have to all the time say in dimension 3 and possibly in dimension 5 and some related question, the answer will be different. Where hyperbolic rigidity is certainly not sufficiently pronounced, essentially because of existence of the mapping class group or thing related to it. But this, what I said, formally independent from that. I formulated a statement in all dimensions, and which are true. In conjecture, you say always true. One of the conjectures, however, that this invariant for what's number of cells in triangulation and depending being only connected to the volume, we know it's true for certain spaces, but for some we know it's false, and this probably rather exceptional where it's false, and this can be isolated, right? But the dimension 3 here only is on the side what looks like exception. So there was nothing special, I was saying, in dimension 3, except it's kind of from this perspective, it's an unpleasant case which has to be looked in much finer detail to give an answer. But there, of course, the complexity doesn't come from the number of cells, but the complexity of its actually entropy type invariant of this and automorphism appearing in the circle vibration. And this is not present in higher dimensions usually. Possibly the theory of nature incorporates both of them, but I am unaware of it. It's not possible. It's not the issue which I touched upon here. Right? Dimension 3 was not here an issue. Yeah, and the question which I am asking is, if we're given hyperbolic manifolds, which is larger injectivity radius, I map it somewhere or low dimensional space, and there is a fiber, always that any Morse function of this fiber has larger number of cells and probably proportional to the exponent of this injectivity radius. There's a conjecture which, when you map to the point, it is with different exponent in the theorem of these two people, right? And so I'm just speculating on their result here, because in all other instances, this kind of estimate lead to this conclusion. So I expect it to be also like that. But it's not. I haven't thought maybe it's not so difficult to prove. Looking at the proof, maybe I'm not surprised. You just look carefully at the proof and say, do this, and see. But I haven't done that, so I don't know how deep it is. And it's easy to figure out if simple argument works or not. Making counter examples may be hard.
So you mean the Bader-Sauer paper, right?
No. I mean the Abraham doesn't. This paper I mentioned because there's instance of waste in convention 2, and this is for special groups. They're also about the waste. So it was a recent paper about the waste, so I brought it up. But my major attention is to this group of this paper. What they show is just, in convention 2, just volume. It's usual waste, geometric waste, it's not waste related. It's logical invariant. See this?
Actually, wanted to ask you about you wrote down the paper of Bader and Sauer.
Yeah.
I was very surprised to see the paper that you get kind of.
Yes.
Can you put it in a?
No. This is it. I learned that this paper 4 days ago, 5 years ago. I met him and he told me about that. And so I'm just intrigued. So I probably linked it up because certainly it's about it fits in this discussion. But I haven't. I look at the paper very superficially. So it's certainly in the same world, and certainly it has the same.
Can you even imagine to see some property of the fundamental group which will imply inequalities like that in codimension 3, 4, etc.? Oh, it's
no. How to say? I just learned about this a few days ago and haven't given any thought. I certainly it fits into this topic, so I brought it up. If you start thinking about that, you have to look at this paper. But I only look at the form of the statement and just very superficially. And the proof very superficially, and it's a little bit kind of on the verge of what is true. Yes, nearly kind of almost trivial argument, but just works. Yeah, and what I can say, but it works amazingly. It's rather amazing. It works, and we don't know what happened for higher codimensions. So here, on the contrary, what I was saying is not codimension 2, but dimension 2. It's a typical situation. No, there are difficulty. Dimension, codimension can be dual to each other. And now in dimension 1, codimension 1, the easiest is dimension, codimension 2. So here I prove some theorem on dimension 2, and they have proven codimension 2. I don't know how they're related, yeah, but it's usual kind of phenomenon. And when you go next, usually the thing breaks down. opposite. Number 2 is exceptional, right? It's not really a usual number.
Any question? If not, I want to thank Misha not only for the talk, but Mikhail Gromov is probably the person who contributed to our area more than any other area. And we are all we are happy to hear that there is another long manuscript on the way. I'm sure that a generation of mathematicians will build their career on developing that new manuscript. So
No, this, no, I mean, I'm not writing anything. No, I'm not writing any
I thought
manuscript.
you said that you wrote something MG.
No, they're written.
What?
They're old papers.
Oh, this is an old paper.
Yeah, at least 15 years old, yeah.
Oh, so this one I don't know. Okay.
The last I wrote some
lectures
lectures on biology, I can discuss that, yeah. I don't know what mathematics and biology, I can discuss that, but it's not a lecture.
I didn't know this. I didn't know that.
There were some other papers down in the slides.
Hmm?
Can we see the down?
Ah, see, I close it up.
Okay.
Anyway, thank you very much for everything.